Now, what I'm going to discuss with you today is an extremely important result on pulleys. We are virtually going to use this result like staple food. We're going to deal with a movable pulley. An extremely critical result related to pulleys is what I'm going to deliver to you. So, here we have a pulley. This is a movable pulley, and this is moving up with the velocity Vp. And let's say there could be two particles connected at the ends of the pulley, A and B, one moving with a velocity Va, one moving up with a velocity Vb. What we would try and do is, we would try and establish a relationship that's going to connect Vp, Va and Vb. That's what we are going to do. Alright. Now, the basic premise of this relationship is the fact that the total length of the string will remain constant. We are going to talk of string as an inextensible element. That's the constraint that would help us arrive at a relationship connecting Vp, Va and Vb. Let's see how it goes. So now let me imagine that in a given time. So one thing that you can see very easily from this pulley is, there is a pulley and there is this string. The string has three distinct parts in it. There is a portion of the string to the left of the center of the pulley, there is a portion of the string to the right, and there is a wrap-up length. There is a wrap-up length. Yes or no? Now, the hanging portions of the string will vary in length. The hanging portions of the string will vary in length, but the wrap-up length will remain the same. The wrap-up length around the pulley is going to remain constant or preserved. However, when A and B move, they are going to release lengths along the sides. They are going to release lengths of the string along the sides, which would result in the upward motion of the pulley to maintain the string taut. That's the basic idea. So we'll have an interplay of this length and this length along with the motion of the pulley that will help us arrive at a suitable relationship connecting the velocity of the pulley, velocity of A and velocity of B. Constancy of string length is really the key to this relationship. So now, think of it like this. Forget A and B for a while. Think that the pulley has moved up by an amount xp. Think that the pulley has moved up by an amount xp. Yes or no? The center of the pulley, as if it has got displaced up by an amount xp. P is the center of the pulley. It goes from P to P prime. The pulley has moved up by an amount xp. Now consequently, what has happened is, for the pulley to move up by an amount xp, this end M also moves up by an amount xp. This end N also moves up by an amount xp. That means on the sides, I need an additional length of the string, right? This is xp and this is xp. On the sides, I need additional length of the string. How much of string length do I need on the sides? 2xp. 2xp. Now the string is not extensible, right? I need this additional length of the string on this side and this additional length of the string on this side. That means this plus this. For the pulley to move up, I need xp available on this side and xp available on this side. That means I need 2xp available from the string. Right? So somehow 2xp length of the string would have to be freed somewhere. Okay. Now if A moves up, it would free a certain length of the string. If B moves up, B would free a certain length of the string. Together they would free up the required length 2xp. 2xp which is required. I need additional length of the string on the sides. Where would that have to come from? I can't produce more length of the string. I can free up some length of the string from A, I can free up some length of the string from B, and that will appear as additional length 2xp on either side, ensuring that the total length of the string remains preserved at all times. So, suppose the pulley moves up by an amount xp. That means this length of the string is what is additionally required. I need to free up length xp and xp by movement of A and B upwards so that I can get xp on this side and xp on this side. That means I can get 2xp on the sides. How can that happen? How can get 2xp on the sides? If A by its motion upwards releases a certain length xa, B by its motion upwards in the same time releases an amount xb, and together they release an amount 2xp, which features on the sides of the pulley, right? So 2xp therefore must be xa plus xb. xa plus xb is what happens. Yes or no? So which means if A moves up by 2 centimeters, B moves up by 3 centimeters, A moves up by 3 centimeters, B moves up by 5 centimeters, 3 plus 5, 8, P must move up by 4 centimeters. That is what must happen always. Yes or no? So which means the displacement of the pulley would be displacement of A plus displacement of B by 2. And as far as these displacements are concerned, everything in the direction of the motion of the pulley, let's say in this direction, would be considered positive, and displacement. So xp, xa and xb are algebraic quantities, and they have to be accommodated along with their signs. That means everything upwards chosen positive in this case because the pulley is moving up, and everything downwards chosen negative. That means if A moves up by 10 centimeters and B moves down by 1 centimeter, then xa would be plus 10 and xb would be minus 1, for example. This is what's going to happen, right? Now, if I differentiate both sides with respect to time, then if I differentiate xp with respect to time, what am I going to get at a given instant? I'm going to get the velocity of the pulley at that instant. So velocity of the pulley at that instant. And if I differentiate xa with respect to time, I'm going to get the velocity of the end A of the string. So if I differentiate xb with respect to time, I'm going to get the velocity of the end B by 2. This is what I get. So velocity of the pulley would be the average of the velocities, average of the algebraic velocities at the ends of the string connected to the pulley. That's important. Vp would be Va plus Vb by 2, which means, you know, if I had, say, a pulley moving up with a velocity Vp, this end A moving up with a velocity 16 meters per second, and this end B moving up with a velocity 4 meters per second, then the velocity of the pulley would be 16 plus 4, 20 by 2. That means 10 meters per second. Suppose I had this pulley, and suppose the pulley is moving up by 8 meters per second, and this end A has a velocity 4 meters per second. This end B has a velocity V that I want to compute, then this 8 must be V plus 4 by 2. That means V turns out to be 16 minus 4, 12 meters per second is what happens to be. Yes or no, right? In fact, suppose I had A moving up with a velocity of 4 meters per second and B moving down with a velocity of 2 meters per second, and I want to find the velocity of the pulley. The velocity of the pulley then is going to be in the direction of Vp, everything positive, Va, which is 4. Vv, now I'll choose as minus 2 because it's opposite to the direction of Vp, minus 2 by 2. That makes it 1 meter per second. 1 meter per second. Yes or no? Suppose I had this was my pulley. It was moving up with a velocity of, say, 4 meters per second, and this end A had a velocity of, say, 14 meters per second, right? And I want to find the velocity of the end B. Right? What would I do? This 4 velocity of the pulley is going to be the average of these two numbers, algebraic average, 14 plus V by 2. So that gives me v equal to 8 minus 14 minus 6 meters per second. That means b has an upward velocity minus 6 meters per second. Clearly means that b must be moving down with a velocity of 6 meters per second. Yes or no? Right? So the important thing is, if the velocity of the pulley is the algebraic average of the velocities of the two ends, if I differentiate this with respect to time, I'm going to get a similar relationship for accelerations. So the acceleration of the pulley would be the average of the accelerations of the ends A. Algebraic accelerations A and B of the two ends. So whatever I've said of velocities will also be true for accelerations. Now suppose I could have had a situation very similar to this, which is like this. Say for example, I could have had, say something like this. This is my pulley, and the pulley moving down with a velocity Vp, and this end A, Va, this end B, Vb, then the same kind of relationship would hold good. Velocity of the pulley is going to be Va plus Vb by 2. Also, the acceleration of the pulley is going to be acceleration of A plus acceleration of B by 2. You might want to explore why this will also happen, right? And again, in the direction of pulley, all numbers Va, Vb, Aa, Ab to be taken positive, else negative, right? So this one relationship will come in extremely handy to us. I'm going to give you some illustrations around. We've looked at a mighty important result on pulleys. Now let me illustrate that with some very simple basic examples. So we have this system of two pulleys. This is a fixed pulley and this is a movable pulley. All right. This mass m1 is known to have an acceleration 10 meters per second squared upwards. This mass m2 has a downward acceleration of 25 meters per second squared. I want to find the acceleration of mass m3, which is a3. So essentially I need a connectivity between a1, a2 and a3. Now first things first. Look at this string. There are two strings. This is one string and this is another string. Look at this string, right? If this mass m1 goes up at the rate of 10 meters per second squared, this pulley, which is integral with this mass, right? The amount by which m1 would go up is the amount by which this pulley will come down. Yes or no? This pulley will come down. That means if the acceleration of this is 10 meters per second squared upwards, the acceleration of this pulley is going to be also 10 meters per second squared, but downwards. Yes or no? Right? And that in turn, AP, the acceleration of this pulley, from what we learned, would be A2 plus A3 by 2 is going to be A2, which is 25 plus A3 by 2. So that gives us A3 equal to 20 minus 5, which is minus 5 meter per second square. Now 5 meters per second square downwards means M3 actually is moving up. M3 is actually moving up with an acceleration of 5 meters per second square, because I've got downward acceleration. I've chosen this as downward. Downward acceleration of minus 5 meter per second squared is like an upward acceleration of 5 meters per second squared. So M3 is moving up with an acceleration of 5 meters per second squared. Let's look at this example. So again, I have a fixed pulley and I have a movable pulley. This mass m has an upward acceleration of 20 meters per second squared. I want to find the acceleration of this mass m2. Now realize this pulley has the same acceleration as this mass m2. So this pulley essentially then has a downward acceleration of a2, Now look at the ends of the pulley. This end, so this pulley could be conceived to be something like this. This pulley, I'm talking of this pulley, say call it P, movable pulley, P. It has a downward acceleration of A2, which is synonymous with the acceleration of this mass, and A2 is what I have to compute. Now, this mass M1, what I do is I straighten this up. If I straighten this up, then it's as if, this is my M1, If I straighten this up, it's as if M1 has an acceleration of A1 like this. M1, right? Think of it to be straightened up. I look upon this and I straighten it up. If I straighten this up like this, this entire thing I straighten, then this has a downward acceleration A1, and this end has zero acceleration. The other fixed end has zero acceleration. Very clearly then, A2 must be A1 plus 0 by 2. So in this case, A2 must be 0 plus A1 by 2. A2 must be 0 plus A1 by 2, and A1 is 20, so that makes it 10 meters per second squared. So A2 turns out to be 10 meters per second squared in this situation. Let me look at another situation like this. I have two fixed pulleys and one movable pulley. The velocity of this mass A is 10 meters per second upwards, and the velocity of this mass is 6 meters per second downwards. I want to find the velocity of this pulley. Again, what I do is, think of this pulley with center C that has a velocity V like this, and I end up straightening the string. So if I end up straightening the string, it's as if the end A has a downward velocity of V1, which is 10 meters per second, and I also straighten this up, the B. So when I straighten this up, B, when I think of this to be straightened up like this, then V2 will go up, right? If I turn it like this, straighten it up, B is up. So B, velocity of B would be 6 meters per second upwards. V2 is going to be 6 meters per second upwards. And then I have V equal to, I'll take everything in this direction positive. So V1, which is given to be 10. And then I'll take, since this is upwards, then I'll take minus 6 for this. So 10 minus 6 divided by 2, that makes it 2 meters per second as the velocity of this. Yes or no? I hope you're getting comfortable. In a little while, I'll give you a few more illustrations. I hope you're setting your feet rock solid on the pulley premise. Another illustration on pulleys of consequence and of utility is the following. I have a system of 3 pulleys connected to a block, and this pulley is fixed, whereas B and C are movable pulleys. And of course, there are these strings that are fixed to the pulleys. This free end, call it P, is moved down with a velocity of 14 meters per second, is pulled down with a velocity of 14 meters per second. What would you expect? If this is pulled down, you would expect the block to move up. You would expect the block to move up with a certain velocity, V2. We want to be able to precisely find V2. This is what we want to do. Right. Now, notice, let's start from A, and then we'll go to B, and then we'll eventually go to C and reconcile V2. Now, if I look at this pulley, this end has a velocity V2. This end of the pulley, this end of the string has a velocity V2, synonymous with that of the block. Now, if this end has a velocity V2, that means if this point goes up by an amount V2, then the end B will go down by an amount V2. Yes or no? That means the pulley B has a downward velocity V2 because it's integral with this point, right? In commensurate with constancy of string length, right? This is one string. So if this point moves up by an amount V2, this would go down by an amount V2. That means the velocity of B is going to be V2 downwards. So let me look at B. B has a downward velocity V2. Now, this end of B has a velocity V2. Again, this end has velocity V2, right? That means if I look at B, this end, that means let me call it D. D has a velocity V2 upwards. Now, I want to be able to find in terms of V2, so this has velocity V2 downwards. I want to find the velocity of C. That means this end, C, which represents this pulley, C, let's say, has a velocity VC downwards. Now, again, can I not say V2 plus Vc by 2 must be V2, right? This V2 must be, okay, no, I'm sorry. This V2 must be everything downward positive, I'll say Vc, but this I'll say minus V2 because it's upwards, opposite to the direction of motion of the pulley. Vc minus V2 by 2. Yes or no? So that gives me like a Vc equal to 3V2. That gives me like a Vc equal to 3V2. Yes or no? So good. So now I have this pulley C moving down with a velocity 3V2. So let me focus on the pulley C. Pulley C is moving down with a velocity 3V2. And look at this end E. Look at this end E. This is integral with the block, so it has an upward velocity V2. So this end, call it E, has an upward velocity V2 because it's connected with the block, which is moving up with the velocity V2. And this end P has a downward velocity V1, which is given to be 14 meters per second. Good. There we go. I apply the pulley relationship 3V2 equal to, now this I'll take as minus V2 plus V1 by 2. Yes or no? Yes or no? So that gives me that gives me 6V2 plus V2, 7V2. V1 is 7V2 is what I get. And V2 therefore is going to be V1 by 7. V1 by 7. V1 by 7 means 2 meters per second. Do you realize such a powerful tool it is? Such a powerful tool indeed. Let me illustrate a few more in a little while. Thank you so much. Bye.